Listen to that. So we're doing number 13 first. So let's see, number 13. I don't know which one that is. Whoa. Whoa. We did this one. We did this entire thing. Who asked for this one? Okay. I'll do it, but I mean, I think I even posted the notes on it, so we'll put that down there, and away we go. So the way this problem is done is a combination of conservation of energy and net force. So the person leaves the ice ball or whatever it is in this problem when their normal force goes to 0. So the conditions for that to happen are net force equals mv squared over r, where this is r. And we are measuring things relative to this angle that they gave us in the problem. And when I look at this, there is a normal force acting in this direction and weight acting in this direction. For us to reach the condition where the net force is going to contribute to them leaving, that's when the normal force goes to 0. That's when this component of the force, mg sine phi, is the only force that's acting to keep them in circular motion. That's the condition that has to be met. So as their velocity increases, and this force does change because the angle's changing, but this force is getting smaller the whole time, that'll eventually go to 0. And when rg sine equals v squared, there. That's the condition of how when they leave. Questions about that part? All righty. So now that we know that part, I'm glad no one was really paying close enough attention because I screwed it up. It's not sine, it's cosine. But you know, it's good to know that everybody's on the non-same boat. But cosine. The sine component is the one that's making them go faster. It's down the ramp. But all right, so just set that aside for a minute. We got to figure out where they acquire this velocity. They acquire this velocity because of the change in their potential energy. They start with a potential energy equivalent to mgr. And then when they have slid to here, they have a combination of potential energy based on their new height, mgh, plus their kinetic energy, 1/2 mv squared. Their new height is this distance, but our angle is measured relative to here. So using that angle to get this height, I'd point out that this height could be using this angle, and that makes it the cosine as well. So h is going to be mgr cosine phi, still plus 1/2 mv squared equals mgr. Okay, get rid of all the m's, and we'll have gr 1 minus cosine phi equals v squared rg cosine phi. So we can cancel out the rg's, and now we've got 1 equals, I forgot this 2, didn't I? There. So I'll slide that in there. That's what I get for being all cocky and trying to go through this really fast. So I have 1 equals 3/2 cosine phi. So cosine phi equals 2/3. 47 or 48 degrees. So I don't know who asked about the problem, but boom, there it is. And like I said, we do a much better job in class. So I would look at the one that we did in class the other day. James?
I understood they used that symbol to represent the angle. I just hadn't seen it before and didn't know that was something different that meant something.
Oh, there's a B?
No, the one they used to represent the angle is not.
Oh, yeah, just phi, just Greek letter.
Okay.
So, phi, I guess. Yeah. All right, next. That was 13. So now we'll do 12. What's 12? All right. This is the ridiculous kind of question you're going to see on an AP exam because it combines all the right things together. You know, we've got the combination of conservation of energy, a projectile problem, and the goofiness that is, you know, one of these things where you're going to really shoot the block up in a non-frictionless surface to a friction-filled surface so that you can shoot it up around this. It's just ridiculous. But either way, it's the kind of problem that combines enough together where you would see this on the AP exam. So it's worth taking a look at. And moreover, it hits all the right kind of buttons for a problem like this. The only thing that I would say that's a problem with it is that generally they wouldn't show these stark transitions. They would want to indicate that there's smooth transitions here so that there's no loss of energy as it goes from one to the other. But this is 45 degrees. There's a coefficient of friction on this ramp, and we're told this height is, they give us numbers, so 2 meters. And I've got a spring here, and my mass was 200 grams. And the spring is, I have a 1300 Newton per meter spring, and they pull it back 17 centimeters. Yeah, because that's a good distance. We'll go with 17 centimeters. 20 centimeters would have been just too much. So what am I doing? 200 grams. And there. All right, those are all the pieces I have. The coefficient 0.2. So yours are probably different numbers. Ultimately, what they really want is the fact that the block acts as a projectile. They want the range of the projectile. To get the range of the projectile, we need the velocity of the projectile here. We do have the angle at which it's launched, 45 degrees, but we still need this velocity. I'd argue that you have two different ways to get this velocity. You could use the work energy theorem, or you could use conservation of energy. I've been making good arguments about both of them all day. Which one would you guys like to use? I am indifferent.
Work energy.
Work energy? All right, so I see that 3 things do work on the block. The first thing that does work on the block is the spring. The spring does work on the block. The gravity does work on the block. And let me put these all as a W so that we can recognize we're calculating work, not just looking at the energy. And friction does work on the block. There are 3 forms of work being done on the block. When we're done, this will have to be equivalent to the change in kinetic energy of the block. And we know that the block starts with no kinetic energy. So the initial kinetic energy is 0. Whatever kinetic energy it has here, it's the result of these 3 bits of work being done on the block. Questions about that? All right, so this work being done on a block is 1/2 k x squared. The work done by a spring on an object. The force from the spring is in the direction of motion, so it's positive. The work done by gravity, the gravitational force on a block when it is here will be downwards. And the amount of gravity will be mg. It's going to travel this distance, which I don't know, but can surmise is 2 divided by the sine of 45. Okay, so 2 divided by the sine of 45. Now I have to multiply by the angle between the weight and the displacement, which is this angle. And that is 135 degrees. Gravity is going to do negative work on the block. It's going to slow it down, taking energy from the kinetic wave, so it'll slow it down. Work done by friction. Frictional force is going to be mu mg cosine 45. Don't need to worry about anything there. That's how we get to the force friction. Any questions about that? All righty. the frictional force is this way, but the block goes up a distance 2 over sine 45. Those effectively cancel because it's 45 degrees. But I still have to have the angle between the frictional force and the displacement, which is 180 degrees. These have to be negative because of the angles. So they are going to be taking away kinetic energy from the system, but this is positive. You add these three things together, set it equal to change in kinetic energy. That's going to be your answer. Questions about this? All right, that's a good one. That's a good one. That could be on your exam, sure. Once you get to that point, it's a projectile problem. So you use the kinetic energy to get the velocity. So once it's a projectile problem, though, we've got horizontal and vertical, delta y, set it to 0 because it's going to land at the same height that it started from. And my Vy naught is going to be whatever that V is times the, it's still going to be sine of 45. Doesn't really matter here. And my Vx will be V cos 45. And you're looking for, T. You could also use the projectile formula there, the range equation. All right. That's number whatever that is. No follow-up? All righty. Bye-bye, 12. So next would be 11. Moving right along. 11. All right. All right, 11 kilogram block slides 4 meters down the frictionless ramp as shown in the figure, then collides with the spring whose spring constant is 230 newtons per meter. What is the maximum compression of the spring? How the heck am I supposed to know? I'm looking at their answer. And something doesn't seem right. But I don't think that they took into account. The potential energy correctly from what I'm seeing there. So let's see how the problem is supposed to be done. But I'm looking at what they have for a solution, and something seems amiss.
Everything I tried was like, I kept trying over and over again, and I kept saying it was wrong. So.
I don't know what this is. We have the distance to the spring from the block. And I don't know what you guys have, but I have 4 meters. And the angle is 30 degrees. So there's no way around it. The lowest point is going to be based on how far the spring is compressed, X max. That's going to be our lowest point. So when we talk about how much gravitational potential, I was even trying to think, should we do this in terms of work to see if that would be better? But it's not going to change what has to happen here. We're still going to get the same stuff. So the amount of energy we have right now is going to be mgh, where h is measured relative to the lowest position it's going to attain. And that's got to be 4. Well, let me do this different. 4 plus x max, all divided by the sine of 30 degrees.
They didn't do sine of 30. Because I did 4 plus x and I forgot sine of 30 and I got the answer right.
Oh, wait, I'm sorry. I did this backwards. It should be 4 plus x times the sine of 30.
I did do that.
Okay. And that's just a half, but all right, so that's part of it. Then when we get down to the bottom, we're going to have all elastic potential, and that's going to be 1/2 k x max squared. So they have a 0.5 times a bunch of the stuff here, but I don't see how I don't think they're taking it into account that they had to include the change in gravitational potential energy when they reach the spring. Their answer looks like they're not taking that into account. But I get, you still have to do 1/2 kx squared equals mg 4 sine 30 plus mg x sine 30. And that's all this for x. And the only way to do this is by using the quadratic formula. So I'm interested to see how far we are off from their number. Or maybe I just can't read theirs right. They do have a big square root in there, so maybe they are doing. They might be doing the quadratic formula in here.
It says yeah, I did the quadratic formula. It says to round, in the answer it says to round the two significant figures, and then they only round it to one. So like one wrong.
They're showing 1.6 meters as the answer.
On mine, I have different numbers. Wait,
Yeah, I have different numbers than you. Okay.
I have 4 meters and 30 degrees, and it says on mine that the correct answer is 2 meters.
Your math is different.
Oh, okay.
So two significant figures is 2.0. That 0 becomes significant on the other side of the decimal point. So this is how it's done. This is what they're doing. They just have a bit of a roundabout way of expressing it. Do you want to see it done? Do you guys need to see the quadratic formula here?
No.
I don't. But I do want to say that question B on this one, you better be able to do it. You better understand why the maximum velocity is not attained when it touches the spring, but the maximum velocity is not attained until the net force from the spring and gravity is 0. And that one's pretty easy to find the answer to. You're just going to set mg sine theta equal to kx. This will tell you where you achieve the maximum speed, not what the maximum speed is, just where you achieve it. But finding the maximum speed after you know that isn't too tough. Shreyas?
I got this one wrong, even though I did exactly that. It just kept saying I was wrong.
Yeah, it's not.
Yeah, I didn't use forces to get where it is.
I did x is equal to mg sine theta.
And I did it several times, like to be sure.
Oh,
Oh, well.
I'm just looking to see what they did. They have mg sine theta equals delta S times K. That's this.
I have that too. I have it.
They had 0.23 meters for these numbers.
My math was 21 and my spring constant was 140.
Really?
Yeah. And it still said it was wrong every time. I think I just left it blank.
Oh, it did this.
Oh, funny, because I'm looking at all of your responses. And you guys are all over the place. I like the person who put 0. 3 people put 0. I'm just gonna tell you what they have this for the answer, which is why you have to sometimes kind of figure out what they're trying to say. But that's what they have written for the answer. That is this. So I don't know what they're doing. I don't know what they're doing. I don't know why they'd be marking yours wrong, except that they are following strict significant figures. So you have to, to follow strict significant figures, you can't round in any intermediate step, but there's no step to round here. So I don't know. Here, I'll just grant you all credit. Not that it matters if you turned your homework and you did fine. So, yay, that was not fun. So now we're up to 9.
Yeah.
Woo! Number 9. All right. I'm going to tell you how to get to this answer. You could fault me for not teaching you well enough how to do this. And it's on the equation sheet. That's not an excuse, though. So the definition of work, as you know, is the integral of f dot dx. Recognizing that means that a small incremental amount of work is equal to an incremental amount of displacement. right? If you don't take the integral of both sides, you have this before then, right? You guys understand what I'm saying? Which means that the force equals dW dx. Now, we don't have W. We have U. I want to remind you that if an object's potential energy is increasing, that means the force must be against you. Like if you're lifting something, you are increasing its potential energy. That means the force that you're working against must be in the opposite direction. So as an object goes up, its potential energy increases, but the force is downwards. So this has to be expressed as negative du dx. And this is on the equation sheet. So that's what we have to use. So we have an expression for U. It is, I believe, ax squared plus b sine pi x over L. What's that?
I thought it was, I was looking at my derivative.
Yeah, it's sine. So, and then we're going to calculate this to get what the force is. So the force is going to be an expression of negative 2ax plus b cosine pi x over L times pi over L. Don't forget the chain rule.
It should be negative b cosine, etc.
Thank you. Okay, so I talked to some folks earlier today, they forgot the chain rule. So now you just have to put in your values, and they give you several values to put together. I'm just rewriting it so we can kind of see what's here. The values they've chosen are specific to zero out different parts of this. So the first one says, what is the force at 0? Well, the force at 0 takes this term and throws it away. The cosine of 0 is 1. So the answer will be negative b pi over L. That's got to be the answer for number 1. So let's look at the next one, the answer for number B. We're putting in L over 2. So when I put in L over 2 here, I get pi L, I get the L's cancel and I get pi over 2. Cosine of pi over 2 is 0. So that whole term goes away, and I'm left with a negative 2a L over 2, or negative AL. So going on to the next one, when x is L. Okay, so when x is L, I get over here, I get pi times L over L, or cosine of pi, that's negative 1. So I'll have positive b pi over L, but I also have the a term, so I'll have, let's see, negative 2a L minus b pi over L. It's positive there. Yeah, that should be it, right? Those are your 3 answers. Okay? All right. Multiple choice. Multiple choice. And there is something incredibly important here, which I don't want to spend a lot of time on, but I was hoping somebody would finally ask this question. They ask this kind of question quite a bit without giving you a function. So I want you to think of just this part of the function. Leave that out for a minute. But if you had a parabolic function for potential energy, you have what's known as a potential well. We need to explore this a little bit, because an expression like this is often on the exam. And it's often a multiple choice question where they say you have, like, they might have this at 1,000 joules. And they might say that your object has 500 joules of energy. Where is it constrained to move? And what they're expecting you to do is say, well, I only have this much energy, so my particle can only be located between here and here. So these kind of constraint problems are unusual. I didn't bring it up now because they don't have a whole lot of root in reality, but this is how atomic physics tends to be structured, because a lot of the potential energy functions there are potential wells like this. All right. So that's number 9. Number 8. Okay. The Shreyas launcher. Well, I have to pick on somebody. He's looking at his phone. I'm not a big fan of this question, but mostly because the truth is, once I realized we were going to launch Kyle with this last class period, I'm okay launching Kyle. There, something like that. Trying to be careful with it, but there's a coefficient of friction just over here, right? On the straight part of the course. Am I remembering this right? Otherwise I have to zoom in and look. I like the sprint. Now, the truth is, you guys are physics students. Good physics students wouldn't do this. It says the spring shown in the figure is compressed 46 centimeters and used to launch a 100-kilogram physics student. No, a physics student wouldn't be launched by this. A social studies student maybe, but not a physics student. A physics student would know that if you pulled back a spring that had 80,000 newtons per meter, a distance of half a meter, then the force you're going to experience the moment you release the spring is 40,000 newtons. Now, I don't know that you guys have an impression for 40,000 newtons, but let's consider 40,000 newtons for a minute. 40,000 newtons. Oh, wait, no, if you could put it back half a meter, yeah, 40,000 newtons. 40,000 newtons would be equivalent to about 4,000 kilograms, right? The weight of 4,000 kilograms, which at 2.2 pounds per kilogram is about 8,000 pounds. So you release the spring would be equivalent to somebody dropping 8,000 pounds on you from like a centimeter away, just
I
pow.
wasn't confident in my answer.
What's that?
That's why I wasn't confident in my answers at first, because it just looked like.
Like,
really-
you could not do this to a person. Yes, James?
I just looked it up. Apparently that's about 10 times as much force as a human femur would say.
Well, luckily we're not applying it to your femur, but
The femur is the hardest bone to break. So
well, I know, but
their spine's gone.
it doesn't really matter where we apply it. I mean, I want to imagine, here's what we'll do. We'll put you on the table and we'll put a sheet of plywood over you and stack 8,000 pounds of weights on you. No. And it's going to go from nothing to 8,000 pounds instantly. Now, yes, it is true that will fade away over the half meter that you will be launched. But no, you could never do this to a person. Never. This is bad, JoJo, all around. And like I said, no, you would hopefully never launch a human in this way. Although, we have done a lot of stupid stuff to people, and there are a lot of people who really don't believe that any of this is real because science lies. So I think this is it's a person sorter between, I would say those who should, procreate and perhaps those who don't. One ride on this, and you probably will not be able to procreate anymore. So I say Darwin's at work with this ride, wouldn't you? So, no, we're not going to launch Shreyas. Shreyas has potential. He's just more interested in his phone this week than me, and that's been making me feel sad. I'm getting jealous. So, and that jealousy's running deep. It's running deep. So, and I just want to know what he's looking at, because it's got to be good stuff.
I'm reading a book.
What book?
It's called Berserk.
Okay. Actually, you have no idea. That makes it better knowing that you're reading a book. No. Let me understand. Let me just hear me out for a minute. Shreyas probably can pass the test next week. Probably. He's hit some bumps a little bit throughout the year, but he's gotten real strong in the last week. If I know he's just sitting there reading a book because he's already done this problem and knows it, it's fine. It doesn't bother me. It's all the other potential things that could be going on the phone. And the fact that I'm going to have an evaluation next week. Now, I know for a fact that if there was an evaluator room, Shreyas would not have his phone out. I know him I know that kind of person he is. Still jealous. I want to read my book. I'm reading a crappy book right now.
Well, at the bottom of the Marianas Trench, it is 16,000 pounds per square inch. So I don't know how that relates to this problem, but just thought I'd throw that out there.
Well, interesting. You should bring that up.
It was like 8,000 pounds, right? So was it like 2 times as much?
Can't compare these two things. What you indicated was a pressure, and what this is a force. So it is true, we could convert this to a pressure and see what the PSI is by spreading out the force all over this person's back. And that would give us our pounds per square inch. The fact that it's 16,000 pounds per square inch and your body is what? Maybe 1.5 feet wide, 6 foot tall on the average. That's a whole lot of force. Yeah, that's why you would be all, bottom of the Marianas Trench. So luckily, actually, once you get all the air out of you, you're pretty robust. But once all that air is gone, you're done. Your lungs will pop out your mouth or something. So, all right, back to work here. So what are we supposed to find out? Question A is the low-hanging fruit. We don't have to worry about that, right? 1/2 kx squared equals 1/2 mv squared. I don't know who asked this question, but it is the second part of the problem that is interesting. How far up the incline does the student go? You guys have to choose. I don't care. Work energy theorem or conservation of energy?
Conservation.
All right, so we do conservation of energy. When they are here, I see that they have two kinds of energy, gravitational potential, and they have elastic potential because they are, I don't know how high, but they're some height above the reference level. I have to make the bottom the reference level because we don't know how high up on the slope they go, which is why the bottom has to be our reference level, okay? So they're going to go some distance along this slope. Whatever distance that is, we are kind of interested in both the distance and the height. Because when they are over here and they're finally stopped, they will have gravitational potential energy, and they also will have lost some internal energy as heat along the ramp. I want you to know that when I consider conservation of energy, every number in conservation of energy has to be positive. So I am saying the before and after is always going to be a set of positive numbers. This goes against some of the things we would talk about here because when you calculate the work going up the ramp, the work will be negative. But remember, as we said earlier, work is minus the potential energy. So although the work is negative, the amount of energy we have here, positive. Because that energy now exists in the ramp. Fair enough? All right, so these two are pretty easy to figure out. I'm going to have 1/2 kx squared plus mgh. This is going to be mg d over sine 30. No, I did that. That's the second time I've done that. D sine 30 for their height. And for the work done by friction, it's the frictional force times D. So I can't leave it expressed like that. So how about mu mg cos 30? That's the frictional force times D. That's it. Factor out the D's, solve for your frictional, or solve for your distance up the ramp. We had a conversation in sixth period about what does it mean to say, how far up the incline does a student go? I think they're talking the linear distance along the incline as opposed to their height above the ground. I think they would say height above the ground. So, but I can get why that would be one of those things that would be like, well, which one do they want? So that was number 8. Number 5. I don't know. 5? Which one is 5?
Oh, it's the wind.
Oh, yeah. I think Connor's going on a ski trip.
Yes, I am.
Don't you always go?
Huh?
Like once a year, don't you always go?
Mhm.
I feel like you do.
Now I'm going twice a year.
Wow.
I know, upgrade.
Uh,
Mr. Shelley, you need a vacation. Exuding jealousy here.
I've never been snow skiing. What's funny, I lived in Arizona where I could have driven probably 10 miles and snow skied, but I just never did. I didn't, just didn't. I was not very willing to try new things when I lived in Arizona.
Have you
Yeah.
never skied?
I've water skied,
But never like snow skied?
never snow skied. And yeah, they are different. I'm not going to suggest that they're the same at all.
Water skiing's on one singular ski, right?
Depends. I did it on one ski. I think it would be harder to do it on two. The whole idea of having to deal with both of them and them going different places seems like a problem. One seemed all right, but I don't know. Someday. All right. So Sam, whose mass is 66, straps on his skis.
Please pardon this interruption. The winner of the teacher gift card raffle for this period is Miss Warner. Please see Ms. Capman in room 224. Congratulations to all the winners. Have a wonderful weekend, everyone.
Seniors.
There's 130 teachers at this school. I bumped into a guy yesterday coming this way, and I was going that way, and I said, "Good morning," and he said, "That was it." I'm like, I almost turned around and said, "Listen, mother, you can give me a good morning, but all right." Oh wait, that's on the video too. Fantastic! Fantastic! All right, look, everybody at home, they said seniors, and there's nothing I can do to hold these seniors back. They're leaving. Not to mention the fact, I don't want to do this problem, but if you want to see it done, I will finish it after the noise dies down. So I'll give it a second. So you guys, yes, sir.
I tried submitting my mastering, but I don't think it's working. So I kind of have all that.
Okay, so there is a place for you to put that on Canvas. Just throw it up there. It'll say it's late, but just get it turned in. Okay, you guys at home, is there anybody who wants to see this problem? Okay. Bye, guys. Have a good weekend. We're supposed to figure out how fast they're going at the bottom, right? And you guys choose. Do you want me to do this as a conservation of energy problem, or do you want me to do this as a work energy problem?
Work energy.
All right, so there's going to be work done by gravity, right? Then there's going to be work done by friction. Bye, guys. Have a great weekend. And that has to equal the change in kinetic energy. So let's look at the work done by gravity first. And the nice thing about doing problems using work energy is you apply the formula consistently the same way every time, and it takes care of the signs for you. So the weight's downwards, so I'll have mg. The distance they're going to go is the length of this slope, whatever that is. And everybody has different numbers, I think, for these. So I don't know. They tell me it's a 40-meter high, 20-degree slope. So you'll have to do minus 40 meters divided by sine of 20 to get that d. I'm going to write this as d. And now here's the hard part. This is 20 degrees. You need to have the cosine of the angle between this and the displacement. And that's 70 degrees.
Have a good weekend, sir.
You too. Bye-bye. You follow me on that? All right, so that's the work done by gravity. That will be positive, by the way. The work done by friction, mu mg cosine 20 degrees, period. Right? Now that's the force. Now, the next part is the displacement, which is just going to be d, goes down the ramp. And this will be cosine of 180 degrees because the frictional force will be this way, but the displacement is down the ramp. Good? That's it. Those are the only two forms of energy. We add those together and set it equal to the change in kinetic energy, with their initial kinetic energy being 0. And that'll do it. Excellent. Excellent. You good, Arushi?
Yeah, I just had to ask you a question about Common App.
All right, so you probably want to ask that after everybody takes off. All right, no worries. Then bye guys. I'm gonna stop recording this too, so we don't need that on the video.